Okay, so we're doing something a little bit different today. We are doing a live stream on a research idea, and we are basically trying to recap where we are, what we need to do, and yeah. So, should I give an introduction, Joseph? How should I
Yeah, as you
pronounce your
wish.
name?
As you
Yeah.
wish, yeah.
Okay, let's do that. So it's mainly for my own sake, so that I remember where we are. Because so first of all, like I just want to say it once for all. For me, Joseph, this is very interesting and very important. The fact that I may not be sort of engaged is because I have 3 million other things to do. I'm behind with like two papers and some other things. I'm completely swamped. But having another person that takes the lead on some of these things to me is great. In fact, I'm trying like I have the student that now is taking the lead for everything. So I'd like really the program to have different projects and different leads for the different projects, right? And so if you lead this part, I'll be absolutely great. And whenever you want, you say, okay, no, we have to have a discussion. You schedule a meeting, and we pop up. And if we do it online, it's even better because maybe some other crazy person will come and tell us the things that we are missing. So let me share the overleaf so that also Xander can see a little bit of what is this shared in a way that other people can read it. So link sharing is off. Let's see, how does this work? Anybody can edit this project? No, I don't want that anybody can. Can I remove this? No, okay, I can't do that. Okay, I can only like if I share, I have to activate both links, which is that's not good. Okay, so the point is, the observation comes from Joseph. Basically, is a way to generalize the thing that we're doing for the action principle. So we have a manifold that is position, momentum, and time. We have a two form. In this case, we call it W, which basically quantifies the flow. So you have a region. A two-dimensional region, and you want to see how many configuration are flowing through that region. If the form is conservative, then this is the symplectic form, and it's gonna be, let's see if I get it right, this is closed. And if it's closed in a contractible region, we have that it's the exterior derivative. Oh, there is a wedge missing here, right? There we go. Okay, so it will be the exterior derivative of a potential. And then in general, we want to basically say that our flow form is a symplectic form for the conservative part plus a W hat for the non-conservative part, which could be dissipative, could also be driven, could be many things that we still have to understand. Then we have a displacement field that basically tells us where the states are evolving in time. And the constraint is that the displacement field has to be tangent to the flow. So if we have a region that is made on one side for the displacement field, the flow is tangent, it is not through the surface, so that thing is zero. And the observation from Joseph is that I was only talking about this in the context of a conservative field, and of course this has to be valid also for non-conservative systems. So this is basically the thing that always has to be true. And then the other thing is that the only direction that is always tangent to the flow is the displacement field. This is basically the corresponding in, oh, actually, this is not a symplectic form because we are in an odd dimensional space. It's kind of the symplectic form. It's a symplectic form with one direction of degeneracy, which is exactly the direction of displacement field. And then that's the only direction of degeneracy. And then what we're basically trying to do is to use the Hodge decomposition to basically have divide the form in two parts. And I got from Wikipedia finally the component notation for the Hodge dual, which seems to me just the form contracted with this is the volume form, and then the k factorial is the fact that it's just for forms, this k factorial that come out that I hate. And then I found, Yusuf, I don't know if you already found this, that the notation for the codifferential seems to be just the covariant derivative on the first index, sorry, the covariant derivative contracted with the first index of the form, which this would be a completely like natural thing to do. On Wikipedia, it does not show, it doesn't show how and why this becomes this, like the Hodge, the codifferential becomes this. Do you have any intuition for this at all?
I think I have sent something like this at some point. Did you also find this on Math Stack Exchange?
I did not look for it that much,
Ah,
I have to
okay.
say.
So I will look it up because I sent this something like this I had sent to you a while ago in one of my emails, and there was some discussion about this. I don't know if it was exactly this form, but when I was looking for
Okay.
coordinate expression, it was something like this. So I will just check it out. Okay.
Okay, because the fact that the Christoffel symbol come out for me is complete magic at this point.
Mhm.
And so there has to be some kind of geometric intuition for this. I quite frankly do not have it. If you can find it, that would help me a
Yeah, I
lot.
found the link. I found the link. It's from Math Stack Exchange. Do I just drop it here in the comments?
Yes.
Okay.
Let's
Okay.
see if I can find it. And then can I? Oh, there you go. There you go. Okay, so yeah, yeah. Look at that. Okay. And you sent me this, and I didn't like
Yeah, a while
internalize it at
ago
all.
in one of the emails because you had asked for something like this. So
Okay.
I found this, but for me, it didn't give too much intuition. So yeah.
Interesting. Yeah, if there is the coefficient in terms of covariant derivative is I'm confident in this result. Oh, so there is some other post that actually shows how to do it. Oh, there you go. Nice. The internet is great. Okay, so in principle, the calculation should be here.
Well, I should note that in the first link that I sent you, the number one top answer says that the expression given by Wikipedia and the book is incorrect. And then they work out a similar expression, which still has the Christoffel symbols, but looks a little different. So maybe one should have a look at that too.
Oh, okay. So
Yeah, yeah.
is it the k factorial that it's
So where is
where
the
where is it?
last one? Um,
Oh, there is another Christoffel here.
yeah, so the very last paragraph, what he said.
Oh, okay. So this is different.
So then it's a good question, who is right? It was voted top answer.
And this is why, at the end of the day, I always want to have the calculation double checked by
Yes.
myself because it's always like this. Ah, geez. Okay, because on all these things, also there is a problem that when people think about forms, like they think basically as a triangle, while you're doing the tensor, you really think of a square, and so there is a double counting that happens when you're doing one with respect to the other.
Mhm.
And that always I find that it's always wrong. And so that, but that's just like simple notation. Here, the fact that you get something. Okay, so he basically does an example here and shows that things don't work.
So one should check because, yeah, there's not much else written after that.
Okay.
So I
Yes.
agree that the form on Wikipedia and the one that was in the expected result, it looks nicer, it looks tidier. So if we want to paraphrase Einstein that God does not play dice, maybe it can be the correct one, but one should check. One should check the details.
Yeah. Hello, regular shorts. So you see, we have people that come and hang out. Okay, as I said, the first thing to me is really understand these, what the Hodge dual are and the codifferentials are. Because if I don't understand those things geometrically, then the whole point of this should be to understand what's going on, right? So if we write everything in terms of math that we don't have good intuition for, like it sort of defies it's sort of the purpose. But okay, so I'll make a note to check, is this the correct expression? This the correct expression. And let me put this link directly there. See, so href, and then we go here. Stack exchange. And hopefully I put the correct order. There you go. Okay, so that's going to be one problem. Okay, so now we basically have it worked out for the single degree of freedom uh, because it's simpler. And so we have, let's see, where do we start? So this is just rephrasing. Let's see. Oh, here we still have the F instead of the rho.
We used many notations in one of the previous drafts where I was writing for one degree of freedom. There was no differential geometry, so there.
Yeah.
Yeah.
If we could make the notation like the symbols more homogeneous, so that because then here we're talking about rho.
So rho would be then the Laplacian of f. So we were solving Laplacian f is equal to rho. So we have some sort of a distribution of
Okay,
sources
okay.
from
So
that.
it was G because before it was
Yeah,
G. Like
before it was
okay,
g, and
okay.
g should be the
The
metric
metric.
tensor. So
Okay, okay.
this
So
I
basic.
corrected.
Yeah, yeah, yeah. Okay, so we have that the flow is essentially the Poisson bracket with respect to the Hamiltonian plus the gradient of f, and f itself is the source and sink term, or
Um, well, I think that some parts you had written and some parts I have written here. So later on, I definitely put that uh, f should be when you invert the Laplacian. So you solve the Laplace equation, Laplacian
okay.
f equal
So
to.
rho is the source and sink. So f is basically the scalar that you put in top of the Christoffel. That's the idea, right?
Sorry, I didn't follow so much about the Christoffel.
So we have here that rho ABC is equal F, the Christoffel symbol. So F is essentially the scalar value that then becomes, it's basically the component of the volume form that is the source and sink.
Then probably still that is not consistent
Okay,
because
so yeah, we should do that. Okay, but let's get from here. So any two form contractible on the surface can be written as omega exterior derivative of theta plus the codifferential of beta. And the other part, the harmonic part, goes away because we are in contractible, right? That's the
yeah,
idea.
well, one needs to make an assumption, and shout out to my colleagues from the Budapest University of Technology, Gábor Etesi and Abel which also helped a lot for me to understand this Hall decomposition part. So you
Mhm.
need to make an assumption that there are no 2D holes in your manifold. So
Right.
we have to make this ansatz, but I think that this is not too unreasonable from the point of view of what we do. And if, as long as there are no 2D holes, then there is no harmonic component.
Okay, so I just want to have it written. Like it's not that I don't agree with that. I just want it to be written so that it's there. So any two form on a contractible solver. Okay, there is written. Okay, so let's just put a footnote. Footnote. If the surface is not contractible, i.e. there are holes, 2D holes, then there is the harmonic part. Okay, so regular shorts is asking, can I get a brief summary of what you guys are discussing? So we are basically saying this. Suppose that this form is what quantifies the flows in a extended space phase. So we are in position, momentum, and time. And we have a form that basically says how many configuration are flowing through a particular surface. If the flow is Hamiltonian, then you just say that this omega is the exterior relation of theta, and the theta is going to be our potential kind of one form. And this part is zero. And this is essentially how we get the geometrical intuition for the action principle in the project. And now the idea is that we want to add the part here, this beta, which should be the potential for the non-conservative part. And we want, in the simplest case, we want to recover the Rayleigh potential so that we can basically put everything in sort of in a similar vein. But then my interest is also to understand if there is anything beyond that, right? If we can get a general expression or not, what are the constraints that work on this thing and so on. So part of it is understanding the geometry of the Hodge duality so that we can understand what these things are going to mean physically, and then understanding what type of gauge transformations are available for beta, for theta, and how they can cross each other, which is the part that we're still trying to understand. Okay, so I add the footnotes, the like token expressions of function. Okay. There are ways of relating to the covariant derivative. You already had it written here. I am just silly. But in the simplest case, if I understand correctly, delta should just correspond to taking the divergence of the antisymmetric tensor. So yes, for that, well, for some meaning of the divergence, because in principle, yes. We already had it here.
Yeah. So this is really a draft, and there were some older things which still are
Yeah,
kept
okay,
here.
it needs to be recovered. Like, okay, so we first should try to figure out the mechanism, a simple case. And so what we basically want to say, this this is the 1D case in which you're recovering the Rayleigh potential. And then what we basically have is that the Laplacian of beta becomes rho, becomes our density.
Yes. And here I ended up proving all this, and I ended up proving it even in the case where we allow time dependence, although one should treat these two cases separately, as we had done for the 1D case when we didn't use differential geometry. And actually, it turns out that if this beta is my tree form, then the f that we were talking about previously is just going to be beta 1, 2, 3.
Okay, yes, yeah, the component, exactly, yes. And so now, is this rho a free form or a scalar?
So here, a priori, it's a tree form. A
Okay,
priori.
that's what
But
it
then you
looked
get
like.
more conditions that simplify it. And here I made this discussion about if we have 1 degree of freedom, then what is happening. So we actually have an equivalence between rho being a function and the tree form just using this hot star. Because then
Yeah,
if we have just 1 degree of freedom, then this hot star is exactly doing this, taking a zero form to a tree form.
yeah.
Yeah.
And then the point is that when we are in another degree of freedom, a greater degree of freedom, we yeah we don't know exactly what the thing is. At the time, having multiple linkages should not change the fact that storage and shrinking should still be encoded by a function. So this I do not think so, because what's gonna happen? What my hunch is that we're gonna have sinks and sources for the different configuration on the different degrees of freedom.
You convinced me of this previously. So as I said, in this draft, we have also old ideas still kept there, and then later we answered some of them.
Okay.
Yeah, so I agree with you. I think in general, the role should always be a tree form. And then you were also telling me at some point during the summer about an intuition that a lot of these components of rho should vanish. So actually, it should be that if you have many particles, then the only components of rho that should not vanish are the ones where the Q and the P corresponds the same.
Match.
And
Yeah.
I tend to agree with that. Then if we do it like this, in the case where the metric tensor is the identity, this transfers also to beta, this property. So that's not too
So
bad.
I was thinking on the metric tensor the other day, like if there is a justification that has to be the diagonal or not. And I was thinking the following. At some point, we need to be able to get this omega and create some type of, it's not going to be a volume form, it's more going to be a hyper surface form, because it's going to be like a volume form for just the positional momentum, right? And that thing will basically have to be like, if there is a source on sync term, like that's going to be on states, like it's not going to be on one configuration.
Mhm.
And there has to be some type of a product. Basically, it can't get degenerate. Like the volume form has to be non-degenerate. So I do not know whether there is some constraint of the fact that you can create this hypervolume form on omega, and that it means that beta can't do some weird things. Like in the same way that the fact that I can get omega, right? That omega has to be non-degenerate is gonna have some condition of theta, right? Because theta cannot be zero, for example, because otherwise everything would be degenerate, right? And so there has to be always when you do the wedge with itself, like it can never cancel itself out. And so it needs to cover essentially all direction in some way. So I do not know whether if the fact that this hypervolume form is non-degenerate is going to tell us something about what's the role of G while you're doing that. So
Uh, Sorry, I didn't fully understand what is the argument behind the fact that the theta term cannot be zero. So it's not possible to just have essentially something which corresponds to divergence. So since we are generalizing a diff curl decomposition, like a Helmholtz decomposition, if we were in just 3D vector calculus, then essentially if you assume now to be irrotational. So in your Hamiltonian case, you assume that you are divergence free. And what if you assume now that you are irrotational?
yeah,
Then
I'm not saying that. I'm simply saying so. I need to make this omega right now is essentially counting configuration on a single degree of freedom. And I need to be able to, from counting configuration at a single degree of freedom, to go and count the states, which is the product of the configuration of each degree of freedom. Which means I need to be able to wedge this with itself n times. Does that make sense?
but if we just have 1 degree of freedom, then
Oh, then it's already a volume form because I wedge it one time and I'm good,
Okay.
right? So if I'm in 1 degree of freedom, this is already a volume form.
Ah, okay. Then we are
Well,
probably saying
a,
similar
a, a
things.
hypervolume form. I mean, like if we were in phase space itself, right? Then from omega you create a volume form, the Liouville form, and that's the count of states.
Okay.
Good. We need to be able to essentially do the same thing, where there you go. It would be the count of trajectories, right? Because the omega right now is basically telling you the flow of trajectory per degree of freedom, right? For it's a density on a single degree of freedom. Then you multiply all of them together, then you get some kind of volume form for phase space, which basically, since you're adding time, you're counting the trajectories that flow inside that volume of phase space. And so there has to be a condition of non-degeneracy on omega, yes, on this omega, that if you are just in space and momentum, that corresponds to the symplectic requirement that you don't have any direction of non-degeneracy, right? That the only direction of non-degeneracy is so when we are in extended phase space, we need to make sure that there is only one direction of non-degeneracy, and that's the direction of the evolution. So that basically tells us something about theta, for example, because theta, has to have at least one non-zero component for each along each degree of freedom. Otherwise, it wouldn't work. So I'm thinking that there might be something similar or not for beta. And I wonder whether there is a relationship, when you're taking this omega and wedge it on itself to get the volume. I wonder whether the metric tensor actually is playing a role there,
Hmm. Hmm.
right? That basically the metric tensor is going to tell you the orthogonality between the degrees of freedom inside the beta, because when you're making the codifferential, you're doing something there that has to be compatible. So the point is that there may be a relationship between whatever form you put on the metric tensor and the fact that you're able to make this volume form on the other side. But I have no idea. Like that's just it's just a thought.
It's a good question. I cannot answer that either. From what I've done later on, it seems to me that once more, if you make some assumptions of not having holes in your manifold, then you can do this decomposition, this harsh decomposition for basically any metric tensor, because the only thing you really need is that you are able to solve this Laplace-Derame equation. And the Laplace-Derame equation, exactly this Laplacian beta being equal to some given tree-form rho, it can be solved exactly if there are no holes.
Yeah. Ah, very good. So it gives you the right boundary conditions. Okay, which
Well, that's
basically,
another thing that
oh
I
yeah,
had at the final remarks. We should be very careful about extending this because all the classical theory is done on a compact manifold. But I had asked my colleagues, and they said that for sure it's true and can be extended. It's just that it's not written down anywhere nicely to manifolds with boundary. So you should put something like a sufficiently good decay condition at the boundary, and then it can be done.
okay. Okay, let's re-go through all this as they're written. So we start here, and then at least in 3D case, simply from the assumption that there is no t dependence in the certain six and the beta skew symmetric, I need to obtain formally that this must be that form with f equals, and then indeed we have that. The Laplacian is that, and this is the Laplacian of f equals rho. Okay. So f here is a scalar,
Yeah.
and rho is a scalar here, right?
So this was just showing that I can switch between these points of view, at least here in the
Right.
3D case. And later I found the references that this is actually always true, even in higher dimensions, as long as you have a metric tensor, which is the identity. But here I just showed it by hand. because this
Okay,
was
so I'm just looking at here. The row here was a free form, and now here row is a scalar.
yeah. So I have some abusive notation there, of
Okay,
course.
so yeah, we need to clean this up because it's
I wasn't prepared
yeah.
that we got live, so
Oh yeah. That's fine. I'm not don't worry. I mean, hey, we just need to clean up so that the next time, like I can follow with the symbols and not get confused. Indeed, like these are notes. I mean, this is not a paper. These are notes at some point, so it's perfectly fine. Okay, so then the component here becomes the divergence here, yes, and then all the other components vanish, of course, and the only one that survive is the one where all the like where these two matches and the other one and two are different. And of course that helps like that happens on the other cases the defense symmetry is this conclude then we get it from two the time dependent but also get the back the fact that in general case yes because it's a volume form in 3 dimension it's basically a scalar and we are all nice and happy. Finally we see the relationship with the related Laplacian and the Laplacian yes this is where you're basically like in the 3 dimensional case, we are basically making a curl of the divergence and the divergence of the curl. And so, all right, this is yes, there is that relationship, the Laplacian and the curl of the divergence and what is it, the curl of the, no, it's the curl of it's yeah, the divergence of the curl and the curl, no, I never remember what was. No, it was the curl of the gradient and then the Laplacian on the other side. So I should be able to see it here, right? Because,
well, it's a little more complicated. One should be careful when passing here. The only thing that I
okay,
was
no,
aware
it's not the same.
that
Yeah,
we have this Dirac Laplacian, which is exterior derivative applied to codifferential plus codifferential applied to exterior derivative.
right.
But here, if we are in 3D, then the second term that I mentioned must be zero because I am taking beta, who is a tree form, and I'm in 3D. So the exterior derivative of this tree form is zero.
Is zero.
So that's why it's
Okay.
simplest. So here in this part, I really just put a trivial proof of something that is actually true generally, but I checked by hand in the 3D case. So that's
Okay.
basically happening. So here at the last paragraph where I say finally, there I'm mentioning that actually it's true for free, even in higher dimensions, as long as the metric tensor is the identity.
I was getting confused with another relationship that exists in 3D calculus, but it's not the Laplacian, it's the Laplacian on the vector field where you're making the Laplacian of each component, which has nothing to do with what we're doing here. Okay, so I'll delete everything that I was thinking here. Here we're just doing essentially that we're showing that this then becomes essentially the Laplacian on the component.
Yeah.
Okay. So essentially, what we're saying is that we are doing the Laplace theorem. We we are starting with a three form, and then we go back to a three form, and we are essentially doing the Laplacian of the component of the three form. That's what we're saying.
Mhm.
Okay. Okay. So which means do we have the Rayleigh potential recovered like written down that actually this is no we don't right
We had that in the old file that I just sent you as a PDF that is not in
okay
the overleaf. So there I was doing everything by hand with just 1 degree of freedom and vector calculus and without any differential geometry. And there I did indeed recover the Rayleigh potential. Of
exactly
course,
I remember yeah
up to once more figuring out what is the physical manifold or complete configuration space that corresponds to this phenomena. Because again, if you are on unbounded domain, or even in the case of a bounded domain, you always need to put boundary conditions when you recover this f, where again, the f, I mean that it should be such that Laplacian f gives you the distribution. But as long as you pick the appropriate boundary conditions, you do get back the
Okay.
Rayleigh potential. It's just a question of justifying those physically.
So are we ready to just do the full treatment of the one-dimensional case where we basically start with that ansatz and recover everything and show that we're covering it? Because in the 1D case, it's exactly the Rayleigh potential, right? There is nothing else.
Yeah, so I think that that one works out nicely. Yes.
Okay, so that I think we should probably do that, at least so that we have the 1D case completely nailed and done.
Mhm. Let's look up the PDF.
And then there is the issue of this gauge transformation. What happens if we change the metric tensor, meaning that then we may change the Hodge dual and the codifferential. This part I read and I didn't understand, I have to say. Okay, so let's go through this a little bit slow. So we have two metrics. One is just the identity, so it's the Kronecker delta. And then we have another metric, and the delta 1 or delta 2 are going to be the codifferentials, alpha 1 and alpha and beta 1 and beta 2 and so on are going to be the Hodge decomposition of our thing. So we basically say we have two different Hodge decomposition with possibly different alpha and beta, but definitely two different metric tensor. And we want to understand essentially how we can shuffle terms from one side to the other that basically creates a new set of gauge transformation for the same flow. Okay, so that's the goal. Then given a source and sink distribution for the three form, we always get the BI by solving this equation. Now this I don't understand. Do we know that if we make this transformation, the source and sink distributions must be the same?
Well, I mean, I would expect that these shouldn't depend on the metric. It should be part of the model that the source sink distribution doesn't depend on the metric. No?
So here's what I was thinking. So suppose that we have a metric that it's not a metric, sorry, a flow that it's conservative, right? The question is, so in principle, this can be the exterior derivative of an alpha, and so we remove this part.
Yes.
Can I make a transformation such that this part appear? So that this thing could be decomposed not just in a purely non-conservative part, but in a conservative part, but in a conservative plus non-conservative. Can we do that?
So I would say my intuition is really telling me no, but again, I am not an expert on neither this kind of differential geometry, nor really the things that you do with this really getting the right assumptions of physics. But my intuition is telling me that changing the metric should not create or destroy states, no, because that is what we are encoding here.
Right, but what I'm worrying is that just specifying this part is not enough to tell me everything about the physics. So mathematically, if I take the exterior derivative of this, right, this part goes to zero, right? And this part, can
Gives me
it
the
go to,
Laplacian.
eh?
It should give me the Laplacian. Right?
It was gonna give me the Laplacian. So could I have a beta that is non-zero with a Laplacian that is zero?
Okay, so again, this comes back to what I said about the holes. As long as we eliminate 2D holes, then this is what I got from my colleagues, that everything is good. And then you can conclude that actually
Okay.
this only has zero as the solution. So this not having 2D holes is very important in the whole situation.
So if I have 2D holes, I cannot separate in a unique way the part that is conservative from the part that is non-conservative.
Yeah, so I think that in that situation, you can have non-trivial harmonic forms. That's
Interesting. Okay, so we are saying that if the flow is conservative, which means if omega is closed, then this part will have to go to zero, and then I only have this part.
so if you assume that omega is closed, then yes.
Okay. So I can, so this is good news because it was an open question that so I can, as long as I don't have 2D holes, I can recognize, oh, this thing is conservative. And there is no non-conservative part. Okay, good. So I can't trade alpha with parts in beta then. Because that's the thing. At some point I thought that you said that you could like trade things from alpha and beta by changing the metric,
Well,
which
as I am pointing out below, there is something. So we also talked a little bit about this, that although the exterior derivative doesn't depend on the metric, the alpha always depends on the metric a priori.
okay,
And
but it does not depend in a way that I can make a beta appear when there was a zero beta before. That's kind
exactly.
of
So
okay.
that follows from the lines here. That
Okay, good. Okay, let's go through it. Maybe I'm jumping the gun. I'm being impatient, but okay. So then. Okay, so then we're saying, so if what we're basically saying here is that if we like the fact that we're saying that we're always going to have the sink or swim or the sink or the sink source or sinks term is the same, we are basically saying because this is just the exterior derivative of omega, right?
mhm, mhm.
And of course, omega is going to be independent by whatever the composition we get from here. So of course, this is going to be invariant under any gauge transformation because omega has to be. Okay, so now I got it. Okay, good. Okay. Okay, so this has to be the same. And now we're basically saying it's just going to be a different solution based on the different metric tensor that we got.
Mhm.
Okay. And so this is this, and these two are going to have be to the same, but it doesn't have to be that these two are the same.
Mhm.
Okay, so which means that then this part also cannot be the same because omega has to be the same.
Yeah.
And so what we know is that this part is equal to this part plus the exterior derivative of some gamma.
Yes, because the difference will be closed just by this construction.
And it's going to be absorbed by the alpha.
Exactly. So that's the whole idea. And this is the new stuff that I had done, I think, last weekend that I emailed you about. And I noticed that exactly since you can absorb it to gamma, then maybe there is some hope to argue with your idea for the Hamiltonian and to do this similar decomposition that you had done in the Hamiltonian case. But you do it such that if your metric is not the identity, then you can just transform to the identity, slap this gamma onto your alpha, this new alpha, which is the alpha corresponding to the case where the metric is the identity. That is the guy that you transform to make the Hamiltonian appear. That would be
Okay.
the.
Interesting. So again, going back to my same point here, if you say that this is zero for one metric, you're gonna have to say that this is also zero on the other, and then this has to be zero, or like the exterior derivative of gamma is zero, but then this is just a standard gauge transformation.
Mhm.
So the way that I would think about it, so if I am in a dissipative in a conservative part, so these are zero, then I'm just adding or subtracting a gamma which is the exterior derivative, it's a gradient of something. So that actually just correspond to the standard gauge transformation that you would have in the conservative part, which is very, very nice. So that things sort of are playing correctly. But the point should be that then when you have that beta different than zero, you can make a different type of gauge change that is tied, that ties both the beta and the alpha. What is it? I don't know, but
Mhm.
that's what the math says. Okay, so
Yes.
then gamma is determined after gauge conservation the same way that theta was determined in the period. Yes, exactly, perfect. And this thing you're saying has to be closed. And it is this gamma that implicitly is responsible for the change in alpha in the Hodge decomposition. Okay. But the physics is still the same because this is the real the term that we use to go and get the beta. Okay, but then there is already enough for even just the 1 degree of freedom. Like it's already interesting because there is enough of stuff.
Mhm.
I didn't quite realize. Sorry.
Yeah, this is also something I just written last weekend. Since I wanted to restart our conversation after pausing for a few weeks because we were both busy, and I started to write it down like this. And when I wrote it like this, it started to look a lot better than what we thought we had.
Yeah. Cool. Okay, so very well. Then my discussion in the previous section. So here, the only thing that is missing is the computation of what actually happens, like because it's like basically the G is hidden inside the definition of the codifferential.
Yeah.
So if we were able to write this codifferential in a component notation and be sure about it, then we would be able to see what the actual differences are.
So
And
this is yeah.
go ahead.
Sorry. So
No, go
this is
ahead.
what I was saying at the end of this section, that actually due to this argument, maybe we are allowed to only care about the component notation after changing the metric tensor to identity. And if we change the metric tensor to identity, then things work out very nicely, and possibly even some way that can be generalized to multiple degrees of freedom. So this would be my hope. But again, I am saying my area of research was just fluid mechanics and continuum mechanics. So I'm coming from this point of view. I'm trying to always understand that you wish to have a lot of physical intuition as well. So I try
Yeah.
to satisfy it. So this would be just my thought that if you start out with a metric tensor which is different to the identity, then you can transform in this way to the case where it is the identity under these conditions. And then you do the coordinate decomposition just after transforming. And then it seems to work out nicely. And that's what will be at the end of this subsection if we continue.
Yeah, so I'm trying to think. Okay, I should read everything because I'm gonna say the things that you have written in a paragraph later. Okay, so there is discussion in the previous section. Since G1 is the identity, B1 will the form one. Yes, I should note here that since delta one is now just a component by component Laplacian to a cubic tensor, if one is the case in multiple degree of freedom and one makes if one is in the case
Yeah, so I
in
think that this can also be extended to more than one degree of freedom. That's what I was writing here.
you basically say even if you are in more than 1 degree of freedom, you're gonna have that you are always take component the Laplacian.
Yes, and also if you make this ansatz that you were suggesting for the sourcing distribution rule, that the only non-zero component should be when the Q and P correspond to the same particle, so QLPLT, that's what I wrote here,
Right.
then this can be transferred also to beta 1, because you are just solving it component by component, and then you have the same shape, just corresponding to a higher dimension.
Okay, so we have a lot more than I thought then. Right. We basically can say Okay, so then, okay, let me understand this a little bit better. So this, this is the part that we're going to recover because you take the exterior derivative of that, and then you say, okay, I have this, and this will always be, if this is a two form, this is always going to be a three form.
Yes.
And it's going to be a three form, therefore, how many independent components does it have? Oh man.
In general, a lot, and that's why
Yes.
we need to make this ansatz. So I really like this ansatz that you had written to me during the summer. I remember I was on a train in Transylvania and reading it on my phone. So this is very useful if we assume what you said that
So
just
with that handset, do we recover the Rayleigh potential? Like is that the answer to get that? Because the Rayleigh potential is it's basically one function for each degree of freedom, right?
Mhm.
So if there is a, if by any chance making that assumption gives us that, whatever that assumption is, I don't know, but we
Mhm.
can say, oh, that's the assumption that gives us
Mhm.
that case. So it would be interesting in any way, even if we don't have a physical motivation for it.
Okay. So far,
And
what we had written down, sorry, for the radius potential was for 1 degree of freedom, but
right,
since, if I recall correctly, what we should be expecting is just going to be something additive for each of the particles, no?
right.
So then I'm hoping that something can be done. One should check, but I think that it should be something like this, perhaps.
Okay, so but in any case, we basically say, okay, the 1 degree of freedom definitely is gonna recover the Rayleigh potential. Good. So that's we got that. It's as we say in Italian, we'll bring that home, and then we say, okay, we can generalize that, and we get something. Whether it is the Rayleigh potential or not, we don't know. But it's still some generalization. And then if it's not, then it's going to be interesting to understand what it is like. What is it that then the Rayleigh potential are? Because they should like in any case, we should be able to write this this omega, right? And there is going to be some exterior derivative of the omega that is not going to be zero because with the Rayleigh potential we're going to have non-conservative phi. So if that's not what we posit, there's going to be an answer of what it is, and then we can sort of reverse engineering because I say, okay, this is what the Rayleigh potential gives us in terms of the exterior derivative of omega, and then we say, oh, okay, we can just assume this and get that. Okay, so and I believe this follows everyone. So this is still the single degree of freedom, and then we're basically adding the gamma here, but this is just a gauge transformation now. The
Yeah.
F is not changing.
What am I doing here? So, this was just a point of view shift. So I was just examining in the last line exactly that what it does for the alpha. So, the F is corresponding to beta 1. So I'm just mentioning that this is the same omega for two different metrics in two different decompositions. And I'm just noting in the last line how the alpha changes, but by choice, I did.
Oh, okay, because okay, now I get it. That's where I got confused because this is not the beta, this is the codifferential of beta, and
Mhm.
in this case, but still, you said the codifferential of beta should be different.
Yeah, but in the last line, I'm not changing the beta, so I'm not going. Okay, maybe I wrote it in a non-intuitive way. I was just again doing a draft, so I was just recalling essentially in this last equality that we should not forget that the alpha one is obtained from the alpha two in this way.
Okay.
So I'm not switching back again to the two pure points of view. I'm saying I'm happy with this point of view because this point of view is for the beta one, which is generated by this F, which is just the one, two, three component of beta one. And I like
Okay.
this form because,
Yeah, but I wanted to see how the F changes. I wanted to see how the beta changes such that, but yes, or
yeah, but
even
that's
just
ugly. That's
the
an ugly open question.
The
How
what?
it changes. That's an ugly open question.
Yeah.
That's what we were discussing at the very beginning of the stream. That it's gonna depend on the metric in a super ugly way. So that's still our open question. We don't know. We don't know how it changes for an arbitrary metric. I'm gonna try to argue here that maybe we don't need to care.
No, no, I want to care. So sorry, I want to say. So
Okay.
the way that I think about it. So if we're again, it depends if we get a nice expression of the codifferential in terms of the covariant derivative.
Mhm.
Because at that point, what happens is that we're changing the metric, right? And therefore, we're going to change what the covariant derivative is. And so the difference should be that, should be because yeah, but you're also changing the beta. You're changing both the beta and the definition of the covariant derivative. So in principle, right, if the gamma is 0,
Mhm.
you can still have a change between beta 1 and beta 2, right?
In principle.
Right. So that's the type of transformation that I'd like. So basically, I'd like to see the two types of transformation. One where you just essentially essentially you're having this gamma goes inside. So you're basically trading off something from here and putting it in the gamma.
That is the general case. Yes. Yes.
Oh
So
yeah,
that is
that's the general case. Yeah.
what
Okay.
was
Fair
written
enough.
here. That's exactly the general case. And I was saying that maybe this is good because we can be happy with this, because then we just look at this term, say the last term where you have the exterior derivative of alpha 2 minus gamma. And now you apply your logic from your Hamiltonian paper and say that this guy will generate for me up to the gauge transformation the shape that you had for your theta, i.e., induce a Hamiltonian.
Wait a second. I have somebody knocking at the door. Let me. It's gonna be some person that I don't want anyway. Sorry about that. They are doing some work. The electric company, they're cutting trees and stuff. So that actually was important.
Okay.
Okay. So sorry. Where were we?
Do. So I was trying to argue, yes, that now we have this decomposition.
Mhm.
And then after, so I say that for the codifferential of data, we want to have the shape that we get for beta 1 when the metric tensors the identity, because we have this nice shape. And then that induces a change into the alpha 2, which is the alpha 2 would be corresponding to an arbitrary metric tensor. It induces this change exactly by subtracting this gamma. So now we have this alpha 2 minus gamma, who is the new alpha 1. So it's the alpha corresponding to the identity as metric tensor. And now I say that you can just apply your logic from your paper
Mhm.
on the Hamiltonian case and get some sort of a theta which corresponds now to this guy. And this generates your Hamiltonian. And then we get back, of course, the nice structure for omega.
So
We
you're
had
basically trying to argue that we can substitute some F for some H. Is that the idea?
so
No, because the derivatives are different. So this is a derivative in Q and this is a derivative in P. Ah,
yeah, no. So we get this nice structure for omega. So this
Yes.
induces also a Hamiltonian. So the F you always recover from solving the round Laplace equation. And of course, that involves picking a metric. And I'm saying that essentially here, I'm arguing that you can always pick the metric to be identity because
Yeah,
if
yeah.
it,
Yes,
then you
that I
just do
understand.
this.
Yeah.
And then
Okay,
we
so
have this.
you're trying to say I don't want to see what happens when the metric is ugly. I
Hey, we
understand
can
that.
see. I'm totally down to see, but I'm saying that always it is justified to look at it in this shape, and then we have a nice structure.
Okay, you're basically saying that. So all of this, it's your point is saying that the choice of the metric is completely arbitrary.
Yes, under this ansatz that I was saying of not having any 2D holes, because this is exactly
Yeah,
going to guarantee us that we can always solve the Laplace equation. And if we can always solve the Laplace
got that.
equation,
Okay,
always
okay,
different.
okay. And then you say, you basically want to argue, I don't really care what happens when I have a G. Okay, I got it. Because I can always choose it like that.
Exactly. Exactly.
Fair enough. I'm trying to, no, I can't visualize how this is gonna expand for the non-degree of freedom because these are not gonna be flat anymore. These are like gonna be three-dimensional, so it's gonna be a mess for like the two, even just the 2 degree case. This is gonna be a
Um, I think it's maybe not too ugly, right? Because we are still having a two form. So omega is still a two form. It
oh yeah,
doesn't
yeah, it's always a two form. Yes,
It
yeah,
doesn't
yeah,
matter
yeah.
how many degrees you have, it will be a bigger matrix. And I think that I checked once on paper that there is a well justified algebraic expansion for these things, coordinate by coordinate, that I think it will be fine. Exactly. This is where it will come into play that you make the ansatz that we were talking about having a lot of zeros in your sinc source distribution, which will
Right.
transfer also to the beta.
You know what? So now that I look about at this, it would make total sense that this is just going to be a bigger matrix, right? So this in the n degree of freedom, what happens is that this is just an I here, and this is a minus I,
Mhm.
and this is still one H, and this is the QI and the PI.
Yes.
Now here, we probably will still want that there are zeros and zeros
Yes.
here because we want the sort of the definition of states and configuration to remain the same. And so the only thing that needs to change is the flow, which is on the time component.
Yes.
Now, what I think is going to be different is that this is not going to be a single F.
Exactly. Exactly. But this
I
information,
really think these are going to be the Rayleigh potential.
yeah. I also have this feeling. So the having not just one F will come exactly from this ansatz, I believe, that you make, that you assume that you only have non-zero components where Q, L, and PL match up. And from that you
Right.
can recover. So each of these will give you one F, one
Yeah.
extra F, and there will be nothing else. And that's my intuition.
Okay, so we basically got it. You were saying is we basically
I was
got it.
taking the last email. So, okay, maybe this is a big YouTube party to announce that we got a lot of things. Copyright.
Yeah. Okay. So like it really is just a matter now of just writing it down nicely
Yes.
and that's it.
And checking also the multiple degree Rayleigh potential, but I think it will work because of this. So it's really not. If we recall what we had essentially for the 1 degree of freedom, it was some p square, so momentum square times constant. And then I
Yeah.
think it should be a linear combination of momenta squared for the
Yeah.
general case. And we should, of course, check carefully, but
Yeah.
I think that's roughly it.
Good. Wow, good. If all the projects went this smoothly and yeah, okay. So I would just suggest that you just, like especially the first degree of freedom, like put it all nicely
Yeah.
and then see what you can get for the multiple one. And yeah, for now, don't even bother. Like I'll just buy your argument. The G is arbitrary, so we can choose it diagonal, and who cares? And yeah, yes, because yeah, it would be nice to understand what are those other gauge transformations and so on. But if really the price in the problem is so overspecified that you can basically choose whatever you want, then it's just like it's like the alpha, right? We picked the gauge such that it's p0 minus h, and we're picking a gauge on the beta such that the things are nice and tidy.
Mhm. Yeah.
Good. Anything else?
No, I think then we're good. I'm happy that you agree.
Yeah. And I have to run because I have another appointment at the university at 11. But if there is questions from the chat, if I have 5 minutes, we're doing this crazy thing of doing these things on YouTube, which gives me pleasure because now it's recorded. Like our breakthrough are recorded.
Yeah.
Anyway, yeah, I think that there are no questions coming, so let's just put a pin to it. Alexander, do you have any comments since you are online or you have been quiet?
Well, congrats on figuring this out. It looks very nice.
Thank you.
Thank you. Okay, so let's just close it. And as I said, Joseph, when you have something, we set up another meeting and we'll continue.
Yeah, I will start writing because luckily next week I should have more free time than usual with all my duties here in Budapest. So I will
Good.
get this because now I'm super motivated to put it down nicely.
Very good. Okay.
Yeah.
Bye to everybody then.
Bye.
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 There we go. It's mainly bye.